Today's lecture is on linear approximation. So we are going to start this is the equation of a tangent line to write to anywhere. And so we're going to manipulate this around a little bit. Okay, so instead of y minus y1, I'm going to add the y1 to the other side and move it. I'm just going to have basically y by itself. So then this would be plus y1 on this side. And then let's say that we don't know what our x, or let's just say that x equals a, right? So if the x1 is a, so I'm going to replace here this x1 with a, so this is the x we're going to use, then if I wanted, so this must be the point a, f of a, right? We don't know what, we don't know what f is. We're not supposed to know what f is. We don't really care what f is. But if I had this equation and I was like, okay, I really want to write the equation of a tangent line to a f of a to some function f of x, then I would replace these. Okay, so my x1 becomes a. My y1 really is f of a, right? So this y1 is really just f of a. And for the derivative, right, so the slope of the tangent line is always the derivative evaluated at that point. So we can call m f prime of a, okay? So this is an equation of the tangent line. It's just in a slightly different form. And this form we call the linear approximation form, or sometimes it's called the linearization formula. And a lot of times the y we call L of x because we call it linearization. But this is essentially the equation of a tangent line to any given point, okay? So let's give it a function f. So let's say f of x equals, let's say it's equal to x cubed, okay? So we need to give it a number here so we can see it. Let's say we want to look at where x equals 1. Okay, so that's good because I got an a as 1, so that's perfect. So this equation of my tangent line, so it's doing all the hard work behind the scenes. Since I called it f, it's already figured out what f prime of 1 is, and so it's filled in all these numbers, right? So I know that f of 1, right, so this part would just be 1 because 1 cubed is 1, and then this is x minus 1, and then the f prime of a, so that would be, f prime would be 3x squared, so if I put 1 in for the x, I would just get 3. So in the end, right, really, this is doing all the hard work, but this is 3 times x minus 1 plus 1. Okay, it's basically what this equation of the line is, but it'll, if I change my a, it'll do it again. So what I really want to point out, and we've looked at this before, is that if I was around x equals 1, right here is approximately where x equals 1, the blue line, which is the original function, and the red line, which is the tangent line, are literally on top of each other. So what that means for us is we can actually use the tangent line to approximate things like around 1. Like for instance, what if I wanted to an approximation for what if x were 1.1? Like it looks like they're about the same, so if I put in L, this would be my tangent line approximation. It's going to do all the hard work for us. 1.1, right? We get 1.3 as our approximation. Now the actual f of 1.1 gives us 1.331. So we're pretty close here, right? Our linearization gives us 1.3 and the actual is 1.331. Now you may be thinking to yourself, like, why? Why would I be doing this, right? If I can just plug it in to my calculator and it's going to give me this, then why do I need this? Well, this is actually what your calculator is doing, right? So this is kind of the behind the scenes. It's approximating all of this, kind of using this information. And really, when you get up into much harder functions, sometimes multivariable functions, sometimes a linear approximation might be the only good way to approximate at a value or a point, okay? So this is our linearization formula. It's essentially the tangent line in a slightly different form, just written more formally in calculus notation, and we are going to use it to find approximations around. So basically, We have an x, right? We choose an x that we know that's easy, that's around the thing I want to approximate, which is 1 in this case. And then that would be we start out with f prime of 1, x minus 1 plus f of 1. And then in the end, we just replace the x essentially with 1.1, and we get our approximation. So let's look at another one of those, okay? All right, so this time, here's our approximation formula. It doesn't have an f or anything. We want to approximate, or let's do the linearization of the square root of x at x equals 4. Okay, so that means my f of x, I said, was going to be, I'm just going to say the square root of x. Okay, and we want to approximate this around 4. Okay, so we want to write the equation of the tangent line. Now I know that my lovely Desmos thing will actually do this and fill it all in for me, but let's actually do it. Okay, so I'm going to say L of x equals, so f of a, we're going to use a equals 4 in our case. Oops, not 5. So so if I have f of a, that's f of 4. So I plug in 4 here, and the square root of 4 is 2. So my f of a is 2. Now I just have this in I wrote my f of a first this time instead of plus, but it doesn't matter. Addition is in any direction. So I have 2, and then plus. Okay, so now f prime, if this is f, then the derivative of x to the 1/2 is 1/2 x to the negative 1/2, which I'm going to write as 1 over 2 square root of x. So that is my derivative. So I just wanted the visual here. So when I plug in 4, my f prime of a, if I plug in 4 down here, I'm going to get 1 over 2 times the square root of 4. And the square root of 4 is 2. So what I really have, my f prime of a is 1 over 2 times 2, which is a 4th. So I'm going to replace this then with a 4th. All right, and then this is just x minus 4, right? All right, so there's my linearization. So I'm going to take that back away. I was just using that for a second, and we will call this our f of x. Okay, so let's zoom in here at x equals 4. And again, like, you can't distinguish the purple from the black, right? So let's use this to approximate a few things. Let's try to approximate x equals 3.96. So since I have it set up like this, right, really I'm going to plug in 3.96 right here, but I'm just going to do L, because I love Desmos, of 3.96. And this is going to give me, what did I do? I'm not sure here. All right. Oh, because I've got this up here. Let me delete that. Okay. There we go. L of 3.96 is 1.99. So let me go back up here and actually call this f of x. So then I can equals. Okay, so then the real f of 3.96 is 1.98, and we got 1.99. So it's a solid approximation, right? They share at least the 1.9 in common. And actually the 8.9 would actually round to 9. So it's a fair approximation. Now, when I'm doing this, right, I wouldn't want to see how it's separating, like up here. Like, I certainly wouldn't want to use this as an approximation for 8. Because what if I put in f of 8, right, and the linearization L of 8, right? Now my graph is, so my f of 8 is really 2.82, but my tangent line is saying that it's 3. So the further that I get away from the 4, the less accurate my tangent line or my linearization will be. Okay, so I need to kind of stay right around this 4. It kind of looks pretty solid for maybe 1 unit in each direction, right? Because like here would be 3, and then here would be 5. So it's fair. Like, I would stay within 1, maybe even a half, and then it would be great. Okay? All right. So again, why are we doing this? It's because this is what's going on behind the scenes in your calculator. And it's always a good thing to know what your calculator is thinking. All right, so let's do one more of these. So I have y equals sine of x, and I want to approximate sine of, let's say we're going to approximate sine of 0.05. Okay, that's what I want. So what I want to do, right, based upon this, I'm going to call f of x equals sine of x. And now this time it didn't tell me what to use as my a, but I can see that 0.05 is very close to 0, right? So let's use a equals 0. Right, so let's write our own L of x now. So our f of a, this first piece here, f of a would just be f of 0, because we're going to use a equals 0 as our approximation. So I'm just kind of putting it up here so you know what I'm doing. So f of x equals sine of x, and so f of 0, this piece right here, sine of 0 is 0, so this is just a 0. And then I have plus, my f prime would just be cosine of x, because the derivative of sine is cosine, and cosine of 0, would this be f prime of 0, would be 1. So this is just a 1 here. And then I get x minus a, or actually 1 is my a, so 0, I'm sorry, so x minus 0. So this is my equation of my tangent line. Now really this is just y equals x, but you can see that when I zoom in really close, right, my lines are of course lying on top of each other. So let me do my approximation for 0.05 using my L function. So I'm going to put in 0.05 for x. Oops, let me call it capital L so it matches. L of 0.05. Oops, that's because of this. I've got to take that away. So L of 0.05 is 0.05. And let's see, my f of 0.05 is 0.0499, right? So there's a lot more here than this one's just approximating to 2 decimals. But if I round this to 2 decimals, I would get 0.049, which would be 0.05 as an approximation. So it's a solid approximation, right? I could maybe go a little further. What if I did L of 0.2, right? So that gives me 0.2. What is f of 0.2? Well, that's still a reasonable approximation, right? L of 0.2 is 0.2, and if I round this up, it would also be 0.2, right? This obviously has more decimals and is more accurate to more places, but for an approximation, this is a pretty good approximation, right? It's just when you don't want to start using this approximation at 0 see how my graph is separating from the tangent line right about here, right, and down here. So it would be a good approximation basically between here and essentially like really right here. So maybe 0.5 in both directions is really solid approximation. This time we're going to use linearization to approximate the tangent of 44 degrees. Now this time they're not telling us A, they're not telling us F, so we have to sort of figure it out on our own. So since we want to approximate the tangent of something, I'm thinking that our F really should be tangent of x, and then we want to choose an A that is close to 44 degrees that we know, which I would say is 44 degrees, or 44 degrees is very close to 45 degrees, which is really pi over 4. So we're going to use our A is equal to pi over 4, okay? Now, the tangent of pi over 4, right, that's f of A, that will be L of L of x is equal to, that will be 1, right? And then we'll just let, so the derivative of secant squared, or of tangent is secant squared, but we'll just let Desmos this time actually give us f prime of pi over 4, which is 2, okay? So that's nice. So I have 1 plus 2 times then x minus our a is pi over 4. And I'm going to close my parentheses. All right. Actually, not down there. How about out here? Okay, so there is my tangent line. So I'll take this one away and this one here. Okay. All right, so I don't need that anymore. I just used it. Okay, so let's zoom in here at pi over 4. Okay, so pi over 4 is right in here, right? And we can kind of see that, well, let's just, so do a decimal approximation for pi over 4 so that we're all on the same page. So it's about 0.78, right? So like right in here, right? It's very close right in here. So that's where it is. So this is where my tangent line is. And so when I zoom in, I can see that really, really close here. I'm good, right? So I'm going to then convert, which I kind of already did here, 44 into radians to put it into my L of x. So like simplified, I think these are both divisible by 4. That would be 11 pi over 45. Okay, so let's approximate those. So first we'll do L of, oops, not the wrong L, L of, I'll just do 44 pi over, so pi divided by 180, so 0.96. And what is the actual version of that? F of 44 pi divided by 80. Ooh, hold on a second. What do I have here? Oh, I did 80, not 180. There we go. Oh, that's much better. Okay, I thought, uh-oh, maybe I'm in degrees. Okay, so 0.965, 0.965. I'm very close, actually, on this one, right, to 3 decimal places. Well, okay, just 3, because then this would actually, maybe just 2, because this would actually round up to 0.97. Actually, it will be 0.966, and this is 0.965. But it's a fair approximation. All right, so let's do one more where we don't know what f is. Okay, so this time we want to do an approximation for 2.001 to the 5th. Okay, so we have to figure out our own function. So I'm saying probably a simple function. F we'll say is x to the 5th. Right? So basically we want to figure out what the function is and then basically a nice easy number for a. So I would say this is very close to 2, so we will use a equals 2 when we write our equation. Okay, so L of x here will be, okay, so if I plug in 2 into my x to the 5th, 2 to the 5th, let's see, 2 to the 4th is 16 times another 2 is 32. And let's see, then I'm going to have a plus. So f prime would be 5x to the 4th. So if I put in 2, 2 to the 4th is 16, and then I multiply that by 5. So I believe that that will be 80. So this is 80 times then x minus 2. Oh, not 3, 2. Oh, I think I have something wrong, don't I, if I'm supposed to be at 2, because it does not look like it's, actually, where is 2? Actually, maybe it is approximate. It's just, oh yeah, it is. I'm just a little bit, ooh, but if I zoom out, it makes it all shrink up together. So that since this graph is very steep right here, it's kind of hard to tell, but this is spread out by 10. So really, like this first one right here is 2. So I'm right in like here. So here's where I kind of can't distinguish them. Let's see, where's my x? So here we go. Now we're really right in. All I can see is the purple, is the linearization. Okay, so I think we found the right one. So let's use it to then approximate 2.001. So I'm going to have L of, capital L of 2.001. And I have to get rid of this one. All right, so that gives us 32.08. And f, the original function of 2.001, is 32.08. Okay, so we're very close right here, right? We could also use it to approximate 1.98 or 1.9. So let's do that while we're here. L of 1.98, as long as I stay close to 2, I should be okay. So what is the original? Okay, so 30.4 versus 30.43. but still a very good approximation. So this is like a nice, easy way of just approximating when you don't want to do the crazy numbers. Maybe, I don't know, maybe you got your calculator wet and it doesn't work anymore and you can do it like this, right? So this is a nice this is called linearization, and it's a way to approximate the value of something using the tangent line. So as long as we stay close to where our tangent line is anchored, then our approximation should be pretty accurate. Okay, that's why we draw them. And this is what your calculator is doing in the background.